Let's investigate the relationship between media and extent of refraction, looking at it now in a more advanced manner in order to verify Snell's law. Remember that Snell's law states that the ratio between the sines of the angles of incidence and refraction is equal to the ratio of the refractive indices of the refracting and incident media. Sine theta 1 over sine theta 2 is equal to n2 over n1, where theta 1 can also be called the angle of incidence and theta 2 can also be called the angle of refraction. And n2 is the refractive index of the receiving medium, the refractive medium, and n1 is the refractive index of the incident medium. Remember that refractive index tells us how much slower light can move through that medium than it moves through a vacuum. So for example, air's refractive index is 1, meaning light travels at the same speed through air as through a vacuum. Glass's refractive index is 1,5, meaning that light travels 1,5 times slower when it travels through glass than when it travels through a vacuum, meaning that glass is a more difficult medium, which we call an optically more dense medium than air is or than a vacuum is. Now the aim of this investigation is to verify Snell's law for light moving between a variety of media. So we want to check whether it's true that sine theta 1 over sine theta 2 equals n2 over n1. But we can also write this in our format of a focus question. How does independent variable affect dependent variable? What do you think in this case are our independent and dependent variables? n2 over n1 is our independent variable. In other words, the relative refractive power, the relative optical density of the two media. That's our independent variable. And how does that affect sine theta 1 over sine theta 2, the relative sines of the angles of incidence and refraction? So we have already collected the data that we're going to use. We did that in previous movies. You can look back to confirm that this was the data that we collected for the investigation where we made the light travel from an optically less dense to an optically denser medium. And we can liken this to what happens when a trolley is moved from tar, an easier, to gravel, a more difficult medium. You only get refraction when you get light, or in this case a trolley, reaching the boundary between media at an angle. Head on, it won't cause refraction, but at an angle, we get bending, we get refraction. Why? Because one side hits the boundary before the other, and in this case, it slows down before the other side does, before the other wheel does, and that causes the bending. And when the motion is from an easier to a more difficult medium, the refraction is always towards the normal. And the more different the two media are, the more pronounced the bending is. So when this trolley moves from tar to stone, rather than gravel, its path will still bend towards the normal, but more so than with the gravel because of the greater difference in ease of movement between the two media. And similarly, we found that here, that the greater the difference between the two media, the more the bending happened. And this is the data that we found. So N1 in all of those cases was 1 because we controlled the incident medium as air, which has a refractive index of 1, and then we varied the refractive index of the receiving medium, the refractive medium, and these are the values that we chose. In all cases, our angle of incidence was 30 degrees, and you can look back and see that this is the data that we measured. So we found a smaller angle of refraction for the more optically dense receiving medium, remembering that that meant a greater degree of refraction, greater extent of refraction. Then we did an investigation where we let the light shine from an optically denser medium into an optically less dense medium. And we chose to control that receiving medium as air. And we varied what the incident medium was. And we found that in all cases, the light got refracted away from the normal, and more so the greater the difference between the two media. And that makes sense. As we can see in our analogy, if we have a trolley moving from a more difficult medium to an easier medium, like from gravel to tar, the wheel that reaches the boundary first can speed up for a period of time while the other wheel is still going slowly, and that causes bending of the path of motion away from the normal. And the greater the difference in ease of movement between the two media, the greater that bending. So if we use stones rather than gravel, but still have tar as our receiving medium, we get the same effect bending away from the normal, but now the wheel that stays behind is going much slower than the wheel that's ahead for that period of time before it also reaches the boundary, causing an even greater degree of bending. So the greater the difference between the two media, the more pronounced this refraction is. And that is also what we saw here. So we put this data into our table. So first of all, just remember that N2 was now controlled as air, with the refractive index of air being 1, and we varied what the incident medium was, and therefore N1 varied between our treatments. In all cases, we used an angle of incidence of 30 degrees, and these were the measurements that we took. So now what we need to do is we need to convert the information that we have into what we need to answer this question. What is the relationship between N2 over N1 and sine theta 1 over sine theta 2? So the first step is to work out N2 over N1. So all we need to do is to divide N2 by N1. So obviously 1 divided by 1 is 1. 1 comma 1 divided by 1 is 1 comma 1. Please continue. Pause the movie until you've completed that column. And this is what you should have got. For the first view, it's really easy because you have 1 at the bottom of the fraction, and so obviously the answer is just simply N2. But then be careful, because later on we have 1 over 1 comma 1, 1 over 1 comma 2, and so on. You can verify this with your calculator if you haven't done it already. The next thing we need to do is to calculate sine theta 1, sine theta 2, and then divide sine theta 1 by sine theta 2. So we start by writing sine 30 equals on our calculator, and we get the answer 0,5. Notice that all the angles of incidence were 30 degrees, so sine theta 1 is going to be 0,5 for all of our readings. Next, you need to calculate sine theta 2 for each of the different theta 2 values. Pause the movie until you've done this yourself, and this is what you should have found. Next step, we need to divide sine theta 1, 0,5, by sine theta 2. Pause the movie until you've done this yourself, and this is what you should have found. Do you notice anything? Take a look at these two columns. Do you see that they are identical? And that gives us the answer to our question. How does N2 over N1 affect sine theta 1 over sine theta 2? What is the answer to that question? Let's also plot this data in a graph. So here I have plotted the data, but what I haven't done yet is put in the labels for the two axes as well as the heading of the graph. Pause the movie while you fill in the gaps. The independent variable here is N2 over N1, and the dependent variable sine theta 1 over sine theta 2. So this is a graph showing the effect of N2 over N1 on sine theta 1 over sine theta 2. And what do you notice? We have a straight line. We have more than a straight line. Every x value is identical to its corresponding y value. Not only are these two variables directly proportional, they are equal to one another. So what is our conclusion? How does N2 over N1 affect sine theta 1 over sine theta 2? The two are equal to one another, and that is what Snell's law states. So we have verified Snell's law for a variety of media. Sine theta 1 over sine theta 2 is equal to N2 over N1. Now notice this can be rearranged into another kind of format. N1 sine theta 1 is equal to N2 sine theta 2. All we've done is cross multiplied.